In this video lecture, we will discuss the properties of AC circuits, which are linear circuits where sinusoidal signals are used as a stimulus. By the way, the acronym AC is for alternating current, referring in particular to signals that periodically change sign. We will introduce the properties of linear circuits, and then we will discuss the concept of phasor as a tool for manipulating sinusoidal signals in AC circuits. A sinusoidal signal is a periodic signal which can be expressed through a sine or cosine function. In general, a periodic signal p of t has the property that for some capital T and for any real lowercase t, P of t plus capital T is equal to P of t. Capital T here is called the period of the signal. A sinusoidal signal V of t typically takes the form V of t equal to A, the cosine of omega t plus phi. In this function, A is called the amplitude of the signal, omega is called the angular frequency, and phi is the phase of the signal. The amplitude A corresponds to the peak value of the signal. The period t of the signal can be seen as the time distance between two positive peaks or two negative peaks, or between two crossings of the time axis with the same slope. In a signal, the period t is measured in seconds. The frequency f of a signal is the number of periods of the signal that stays in 1 second. So, by definition, the frequency is 1 over the period of the signal. The frequency is measured in cycles per second, or second to the minus 1, or hertz. Note that after a time interval equal to the period, the sinusoidal signal has gone through an entire cycle from A to 0 to minus A to 0 again, and then back to A. This means that the argument of the cosine function, apart from the phase phi, has gone from 0 to pi divided by 2 to pi to 3/2 pi to 2 pi. This in turn means that omega times the period is equal to 2 pi. From this we get that omega is equal to 2 pi divided by the period, or 2 pi the frequency. Therefore, the unit of measurement of the angular frequency is radian per second. Knowledge of the phase phi can be used to provide two pieces of information about the signal. First of all, phi tells us something about the amplitude of the signal at t equal to 0. As a matter of fact, V in 0 is equal to A the cosine of phi. Second, in t0, v of t reaches a positive peak, which means that in t0, the argument of the cosine is 0. Actually, it might be 2n pi, with n a relative number, but let's assume n equal to 0 here. Then t0 is equal to minus phi over omega. So delta t, which is equal to 0 minus t0, is equal to phi over omega, or phi over 2 pi times the period t. So the phase phi tells us the time distance of the signal peak, the closest one to the amplitude axis, from the origin. The phase phi is measured in radians. Suppose we have a circuit consisting of a voltage source VR applying a sinusoidal voltage across a resistor with resistance R. Assume in particular that VR of t is equal to A, the cosine of omega t. Given that, of course, the voltage across the resistor is the same as the voltage generated by the voltage source, the instantaneous power P of t dissipated by the resistor will be equal to VR squared divided by the resistance, which in this case is equal to A squared over the resistance times the cosine squared of omega t. We can define the average power dissipated across the resistor as 1 over the period of the sinusoidal signal times the integral between 0 and the period of the instantaneous power P of t in the t. Or by replacing P of t with the previous expression, A squared over RT times the integral between 0 and the period t of the cosine squared of omega t in dt. Now the cosine squared of x is equal to 1 plus the cosine of 2x divided by 2. Therefore, for the average power, we get A squared over RT, the integral between 0 and t of 1/2 in the t, plus the integral between 0 and t of the cosine of twice omega t divided by 2 in the t. Cosine of 2 omega t has half the period of cosine of omega t, so its integral over a period is equal to 0. So eventually we get that the average power is equal to A squared over RT times 1/2 t, or A squared over 2 R, or the square of the amplitude of the voltage applied to the resistor divided by twice the resistance. The reason why sinusoidal signals are so interesting in electronics is related to a particular property of linear circuits. We still lack a definition of a linear circuit, which will be introduced later on in another video lecture. Nevertheless, it is worth presenting and discussing this particular property here. Let us consider then a linear circuit. We will represent the linear circuit here as a black box containing a set of electronic components connected together to form a circuit with some well-defined characteristics. From this box, we can extract a pair of terminals, which we will call input terminals, and a second pair of terminals, which we will call output terminals. Let us assume that the signal at the input of this linear circuit is a sinusoidal signal. Just to make things clearer, let us assume that the input signal is a voltage signal. This is not strictly necessary, of course. Let's call this signal Vi of t. Vi of t as a sinusoidal signal will be of the form A sub I, the cosine of omega sub I t plus phi sub I. The subscript I in the expression of Vi of t is there just to emphasize the fact that we are talking about the input signal for the linear circuit. In the expression of Vi of t, Ai is the amplitude of the signal, omega I is the angular frequency, and phi sub I is the phase of the signal. If, as we assumed at the beginning, the circuit is linear, then the signal at the output of the circuit, which we will call Vo of t, will take the form Vo of t equal to A sub O, the cosine of omega I t plus phi sub O. So, first of all, if the circuit is linear and the input signal is a sinusoidal signal, also the output will be a sinusoidal signal. Second, the output signal will have the same angular frequency as the input signal. If we had the possibility to probe the current and voltage signals inside the box, the linear circuit, we would find out that all of them have the same sinusoidal shape and the same angular frequency as the input signal. On the other hand, A0 and phi 0, the amplitude and the phase of the output signal, will be in general different from the input amplitude and from the input phase. The way a linear circuit modifies the amplitude and the phase of the input signal is incorporated in the so-called frequency response of the circuit. Note that the frequency response can only be calculated for linear circuits. In particular, the frequency response is a complex function of the angular frequency that, if the amplitude and the phase of the input signal and the operating angular frequency are known, let us calculate the amplitude and the phase of the output signal. A linear circuit can, of course, work also with non-sinusoidal and even non-periodic signals. We will see that we can take advantage of this property of the linear circuits, the fact that they do not change the shape and the angular frequency of a sinusoidal signal at the input, to study their behavior when the input signal is non-sinusoidal. We will introduce the frequency response later on in this series of video lectures. One final consideration for the moment about linear circuits. We said that if we apply a sinusoidal signal at the input of a linear circuit, the output signal is also a sinusoidal signal with the same angular frequency. It is also true that if the response of a circuit to a sinusoidal signal is a sinusoidal signal with the same angular frequency, then that circuit is a linear one. As already mentioned, AC circuits are circuits where all the current and voltage signals have a sinusoidal shape, which means that they can be represented as a sine or a cosine function of time. AC circuits are usually analyzed in the so-called phasor domain, where currents and voltages are represented by means of complex numbers obtained from the voltage and current signals according to well-defined rules that we will introduce in a moment. Use of phasors makes it possible to greatly simplify circuit analysis, in particular by extending in some way Ohm's law to capacitors and inductors through a so-called generalized Ohm's law. It is worth emphasizing here once again how simpler Ohm's law for resistors is as compared to the voltage-current relationship in capacitors and inductors. As we already know, in a resistor with resistance R, the current flowing through the resistor IR and the voltage across the resistor are related to each other through Ohm's law, which is an algebraic relationship. In particular, we know that the voltage VR is equal to the resistance times the current IR. In a capacitor with capacitance C, the current IC flowing through the capacitor and the voltage Vc across the capacitor are connected by means of a differential relationship. In particular, the current IC is equal to the capacitance times the time derivative of Vc. Also in an inductor with inductance L, the relationship between the current IL flowing through the inductor and the voltage VL across the inductor is of the differential kind, with the voltage VL equal to the inductance L times the time derivative of IL. In general, solving a resistive network, which means finding all the currents in the branches and all the voltages in the nodes in that circuit, requires solving a system of linear algebraic equations. In case the network includes also capacitors and inductors, we will need to solve a system of linear differential equations, which is typically a tougher task than in the case of a system of algebraic equations. In the phasor domain, the current-voltage relationship in capacitors and inductors can be written in algebraic form, as in the case of the resistor. This, as we will see, leads to a strong simplification of circuit analysis. One other feature that makes phasors so useful in the analysis of AC circuits becomes apparent when we need to sum sinusoidal signals with the same angular frequency. For the purpose of providing an example, consider two sinusoidal signals with the same angular frequency. V1 of t equal to A1 the cosine of omega t plus phi 1, and V2 of t equal to A2 the cosine of omega t plus phi 2. It can be shown that the sum of the two signals, let's call it V3 of t, equal to V1 of t plus V2 of t, is also a sinusoidal signal at the same frequency as V1 and V2, given by A3 the cosine of omega t plus phi 3. Determining A3 and phi 3 may not be a trivial task at all if we work with the signals in the time domain. Working in the phasor domain, we will see, can greatly simplify this operation. Let us consider now an AC circuit where a sinusoidal signal at a well-defined angular frequency omega is used as a stimulus. We know that all the current and voltage signals in that circuit will have the same sinusoidal shape and the same angular frequency as the one serving as a stimulus. Now, a sinusoidal signal in this circuit will have the form V of t equal to A the cosine of omega t plus phi, where A is the amplitude of the signal and phi is the phase. If the operating frequency omega of the circuit is known, V of t can be unambiguously identified once the amplitude A and the phase phi have been provided. V of t is the representation of the signal in the AC circuit in the time domain. In the phasor domain, the same signal is represented with a phasor, indeed, whose symbol typically is the same letter as the signal in the time domain, just in the capital case with a bar over it. So V bar. The phasor is a complex number that, in the polar representation, has a modulus equal to the amplitude of the signal in the time domain and has the phase the argument of the cosine function in the time domain. So the complete expression of the complex number will be A times the exponential of j omega t times the exponential of j phi. Now, since in an AC circuit the angular frequency is the same for all the signals, in the phasor representation the dependence on the angular frequency is considered as implicit. Therefore, in the phasor representation of the signals, the exponential function of j omega t is removed. Eventually, the phasor representation of V of t becomes V bar equal to A, the amplitude of the sinusoidal signal, times e to the j phi, the phase of the sinusoidal signal. Note that in this final expression for the phasor V bar, the two pieces of information we need to completely identify the sinusoidal signal, the amplitude and the phase, as we said before, are preserved. It is worth emphasizing one more time that in the definition of the phasor V bar, we have just chosen to ignore the dependence on the angular frequency omega because in an AC circuit stimulated with a sinusoidal signal with frequency omega, all the signals in that circuit are sinusoidal signals with the same frequency. So this dependence on omega in all the signals in the circuit has not disappeared, but is simply given for granted. It will show up again when we discuss how to transform a phasor back into a sinusoidal signal. Transformation of a sinusoidal signal into a phasor and vice versa is a linear operation, which means that this transformation preserves the addition of sinusoidal signals with the same angular frequency and the multiplication of a sinusoidal signal by a constant. This can be expressed as follows. Suppose V1 is a sinusoidal signal at angular frequency omega with corresponding phasor V1 bar, and V2 is a sinusoidal signal with the same frequency and the corresponding phasor V2 bar. Suppose also that V3 is the sum of V1 and V2, and that V3 bar is the representation of V3 of t in the phasor domain. Then V3 bar is equal to V1 bar plus V2 bar. So the sum of two sinusoidal signals in the time domain corresponds to the sum of two phasors in the phasor domain. Moreover, if A is a real constant, then A V1 of t in the phasor domain will be represented by A V1 bar. Let us see now how we can go back from the phasor representation to the sinusoidal representation. We know that if V of t is equal to A, the cosine of omega t plus the phase phi, then its representation in the phasor domain will be V bar equal to A times the exponential of j phi. Let's now multiply V bar by e to j omega t, therefore recovering the dependence of the signal on the angular frequency. We get V bar times e to the j omega t is equal to A times e to the j phi times e to the j omega t, which is equal to A times e to the j times omega t plus phi. By applying Euler formula, we eventually get A times the cosine of omega t plus phi plus j, the sine of omega t plus phi. Note that the real part of the complex number we get corresponds to the sinusoidal signal v of t we started from. Then v of t can be obtained from the phasor v bar by taking the real part of it. So v of t can be written as the real part of the phasor v bar times a to the j omega t. Now a little more about the transformation of phasors back into sinusoidal signals. Consider the sinusoidal signal v of t equal to A, the cosine of omega t plus phase phi. The corresponding phasor is given by V bar equal to A, the exponential of J, the phase phi. Consider now the complex number V sub omega given by the phasor V bar times e to the j omega t. This is given by A times e to j phi e to the j omega t. V sub omega is a function of time. In the complex plane, V sub omega can be represented as a vector rotating around the origin with angular frequency omega or with frequency omega over 2 pi. The projection of this vector on the real axis is given by the length of the vector, so the modulus of V sub omega, times the cosine of the angle formed by the vector with the real axis, so times the cosine of the phase of V sub omega. This is equal to A times the cosine of omega t plus phi, which is exactly the signal V of t. Note that as the vector V sub omega rotates around the origin, its projection moves along the real axis, changing its length sinusoidally. This can be seen as a geometrical way to the transformation of a phasor into a sinusoidal signal. Now an example of how we can add two sinusoidal signals in the phasor domain and how the use of phasors can simplify this operation. Suppose we have a sinusoidal signal V1 of t equal to the square root of 3 times the cosine of omega t plus pi divided by 2 as the phase. Of course, if this is a voltage signal, it will be measured in volt. The phasor representation of this voltage signal, V1 bar, will have a modulus equal to the amplitude of the signal, so square root of 3, multiplied by e to the j, the phase of the sinusoidal signal, pi divided by 2. Suppose then we have a second signal, V2 of t, equal to 3 times the cosine of omega t plus pi, and suppose also this is a voltage signal as the previous one. The representation of V2 of t in the phasor domain will be V2 bar equal to 3 times e to the j pi. Suppose we want to find V3 of t as the sum of the two signals V1 and V2. In the phasor domain, V3 of t will be represented by a phasor V3 bar equal to V1 bar plus V2 bar. By the way, we already know that e to the j pi divided by 2 is equal to j, so V1 bar can actually be written as j the square root of 3. On the other hand, we also know that e to the j pi is equal to minus 1. So v2 bar can also be written as minus 3. So v3 bar can eventually be written as minus 3 plus j the square root of 3. Just as a confirmation of the above results about v1 bar and v2 bar, remember that by Euler's formula, square root of 3 times e to the j pi divided by 2 is equal to square root of 3 times the cosine of pi divided by 2 plus j the sine of pi divided by 2. Of course, the cosine of pi divided by 2 is equal to 0, while the sine of pi divided by 2 is equal to 1. So eventually we get j the square root of 3. On the other hand, again by Euler's formula, we know that 3 times e to the j pi is equal to 3 times the cosine of pi plus j the sine of pi. And we know that the cosine of pi is equal to minus 1, while the sine of pi is equal to 0. So eventually we get minus 3. So we found that v3 bar equal to v1 bar plus v2 bar is given by minus 3 plus j the square root of 3. We know we can represent this complex number in the complex plane. The phasor v3 bar can actually be seen as the sum of the phasor v1 bar and the phasor v2 bar in the complex plane. In particular, the phasor v1 bar will be represented by this yellow vector, while the phasor v2 bar will be represented by this red vector. The sum of the two phasors, or of the two vectors in the complex plane, is represented by the blue vector, the phasor v3 bar. Note that the phasor v3 bar is written in rectangular form, with the real part plus j times an imaginary part. We would like to write v3 bar in polar form, as this form makes it easier to transform a phasor back into a sinusoidal signal. Remember that we are trying to find the sum of the two sinusoidal signals v1 of t and v2 of t. Remember that a complex number z can be written in a rectangular form as a plus jb, where a is the real part and b the imaginary part of the complex number, or in a polar form rho times e to the j phi, where rho is the modulus of the complex number and phi is the phase. We know that we can go from one representation of the complex number to the other. In particular, if we want to go from the rectangular to the polar representation, we can write that the modulus of z, which is equal to rho, is given by the square root of a squared plus b squared, while the phase of z, or the argument of z, which is equal to phi, is equal to the inverse tangent of b over a plus pi. This latter definition for the phase phi holds for complex number with a negative real part. We can now compute the modulus and the phase of the phasor V3 to find its polar representation. So, the modulus of V3 phasor is given by the square root of 9 plus 3, which is equal to 2 the square root of 3, while the phase of V3 is equal to the inverse tangent of minus the square root of 3 divided by 3 plus pi, which makes 5/6 of pi. Then the phasor V3 can be written in polar form as 2 the square root of 3 e to the j 5/6 of pi. Therefore, V3 of t, which is the sum of the two sinusoidal signals V1 of t and V2 of t, will be equal to the real part of V3 phasor times e to the j omega t, which is equal to 2 the square root of 3 the cosine of omega t plus 5/6 pi. For each pair of signals V1 and V2, find the sum V1 plus V2 and the difference V1 minus V2 by taking advantage of the phasor properties.